Hello, you're welcome to this lesson. In this video, you are going to learn how to find the higher order partial derivative of multivariable functions. So let's see, I have a function f of xy. Okay, I have this function here. And then I want to find the derivative of this function with respect to x and then later with respect to what y. I can write this as f sub x sub y. This is known as the subscript notation. Okay, and then this is not the subscript notation. So what this means is that you're going to find the partial derivative of this function here with respect to what x and then later with respect to what y. You can write this notation here in a different form. Okay, so I can write this as d squared f over dy dx. Okay, so this is another way to rewrite this expression that I wrote here. This is known as the fractional notation. The fractional notation. So there are difference between these two notations. Okay, so we are going to look at that. For the subscript notation, okay, what that means is that you're going to differentiate with respect to what x and then with respect to what y. So for this, what we do is that we differentiate from left to right. Okay, from left to right. And then for the fractional notation, we differentiate from right to left. Okay, from right to what left. You are going to look at what this means. Okay, so for that reason, let's take an example, okay, so that you can understand what this actually means. So let's say I have a function f of x, y, and then z, okay, which is equal to z cubed multiplying y squared and then ln of what x. Okay, so you have this function here. So what you are going to do is that you are going to find fxx and then y z z. Okay, this is what you are going to find. So for this, you've been given the subscript notation. Okay, so what you are going to do is that you are going to differentiate from the left to the right. So first of all, you are going to differentiate the function with respect to x, and then we differentiate with respect to x again. Then move to y, then move to z, and then we move to what z again. So let's look at that. So we have the function f of x, y, and then z. Okay, which is equal to z cube y squared ln of what x. So first of all, we are going to differentiate with respect to what x. Okay, so that gives us f subscript x, right? So now let's look at that. So for this expression here, it's only the ln that has x in it. So we are going to differentiate the ln. Okay, so in differentiating the ln, we are going to have x prime divided by what x. Okay, times z to the power 3 multiplying y squared. The z to the power 3 and then y squared is considered to be a constant. And you know, x prime is the same as what the derivative of what x, and then that gives us 1. So we're going to have 1 over x times what z to the power 3 multiplying y squared. I can write this as z to the power 3 y squared over x. Okay, over x. So this is what we have now. So from here, we can find fxx, right? So let's find fxx. So you see that you're moving from the left to the right. So we are continuing with this function here. Okay, with this function that I have here. So we got the fx to be z to the power 3 and then y squared divided by what x. Okay, I will write this as z to the power 3 y squared times 1 over what x, which is the same as what z to the power 3 times y squared times what x to the power what minus 1. So now let's differentiate this expression. You're going to have fxx. Okay, you're differentiating with respect to what x. Okay, so that would be, you're going to keep z cube and then y squared as a constant. So you're going to have z cube multiplying y squared. And then now let's find the derivative of x to the power minus 1. That gives us minus x to the power minus 2. Okay, so then you're going to have minus z cube y squared and then x to the power minus 2. Okay, so this is what we have now. So I can write this as fxx to be equal to minus z cube y squared divided by x squared. So now what you're going to do is that you're going to differentiate this function here with respect to what y. Okay, so to do this I will write this as minus z cube over x squared multiplying what y squared. Okay, so now let's do this fxxy. So I'm going to keep this as a constant since we don't have any y there. So I'm going to have minus z cube over x squared. Okay, this is z. I'm keeping this as a constant, then I'll differentiate the y squared. That'll give us what? 2y. Right. So simplifying this, we're going to have fxxy to be equal to minus 2y z cube divided by x squared. Okay, so this is what we have now. So from here, we're going to differentiate this expression here with respect to what? Z, right? So let's look at that. So I'm going to write it as fxxy to be equal to minus 2y divided by x squared multiplying z to the power 3, right? So let's differentiate this with respect to what? Z. So that would be what? fxx yz. So that will be, I'll keep all this as a constant. So that will be minus 2y over x squared. Now let's differentiate z squared. That will give us 3z squared. Sorry, we're differentiating z cube, okay, not z squared. And then that will give us what? 3z squared. So simplifying this, we're going to have minus 6y z squared divided by what? X squared, right? Okay, so now let's differentiate this with respect to what? Z again. So I'll go ahead and then free up some space. Okay, so we have fxx yz, okay, to be equal to minus 6yz squared, okay, over x squared, right? This is what we have now. Okay, so now you're going to differentiate this with respect to what? Z again. So I will write this as minus 6y over x squared multiplying z squared. Okay, so now let's differentiate this with respect to z. So that will be fxx yz, right? So this will be equal to, I'll keep this as a constant. So you're going to have minus 6y over x squared. Then let's differentiate z squared. That gives us 2z. Okay, I use this z here just to differentiate between the 2 and then the z. So simplifying this, you're going to have minus 6y times 2z. That gives us minus 12y z, okay, divided by x squared. So you see that all we just did was differentiating from what? The left to the right. Okay, that's what you just did. Okay, so we are going to take an example for the fractional notation also. So let's look at that. Okay, so we have this function here which is f of xy equals e to the power xy, and then you have to find the third partial derivative. Okay, so what you have here, we have the fractional notation. Okay, so what you're going to do is that you know that for fractional notation we differentiate from the right to left. Okay, we differentiate from the right to what? To left. So what I'll do is that I'm going to differentiate first with respect to what? X. Okay, and then I'll differentiate with respect to what? X again. Then from there, I'll finally differentiate with respect to what? Y. So let's look at that. You're going to have the f, the x. Okay, the f, the x. You're going to differentiate the expression with respect to what? X. So differentiating e to the power xy with respect to x will give us e to the power xy. Now let's differentiate what we have here. Let's differentiate xy with respect to what x. Okay, that will give us y. So we are going to multiply by what y. So we're going to have y multiplying e to the power xy. Okay, so that's what you are going to have. Now we're going to differentiate this with respect to what x again. So that will be d squared f dx squared. Okay, this is what you are going to have. So let's differentiate this expression here with respect to what x again. So I'm going to keep y as a constant. So I have y, and then let's differentiate e to the power xy. That gives us e to the power xy. And now let's differentiate xy again with respect to what x. That gives us what y. So we are going to have times what y. Okay, so and then we are going to have y squared multiplying e to the power of xy. Okay, this is what. Okay, so now you're going to find the third higher order partial derivative. Okay, so that's going to be d cube f over dy dx squared. Okay, so you're going to differentiate this expression here. Okay, with respect to what y. Okay, so let's consider d squared f, okay, dx squared, which is equal to y squared e to the power of xy. So I'm going to differentiate this with respect to what y. Okay, so I'm going to apply the product rule here. So first of all, I'll consider y squared. Okay, then I'll keep e to the power xy as a constant. So let's differentiate y squared. That'll give us 2y. Then we multiply by e to the power of xy. Okay, so now I'm going to keep y squared as a constant. So we are going to have y squared. Now let's differentiate e to the power xy. So we're going to have e to the power xy. Then now let's differentiate xy with respect to what y. Okay, that's going to give us what x. So times x. So simplifying this, we're going to have 2y e to the power xy plus xy squared e to the power of xy. So I guess by now you've seen the difference between the subscript notation and then the fractional notation. Thank you very much for watching this video. Please make sure you like and subscribe.